In this module, we are dealing with moments, skewness and kurtosis. Moments, skewness and kurtosis speak about the probability distribution curve. In other words, these speak about the frequency of different values of x at different points in a distribution. So first, let us see what moments are. Moments are a set of statistical values used to describe the characteristics and feature of a frequency distribution. In other words, moments describe the central tendency, dispersion, symmetry or lack of symmetry, and wickedness of a frequency curve. Moments are the means of various powers of deviation of observations from any statistic of the distribution. When the deviations are taken from the arithmetic mean, such moments are called central moments, and when deviations are calculated from values other than the mean, they are called raw moments or arbitrary moments. So let us see the central moments. What are central moments? There are 4 central moments in the case of a numerical distribution. The first central moment is the arithmetic mean of the deviation. The second is the variance. The third is skewness. And the fourth one is kurtosis. Let us see skewness and kurtosis in a little detail. Skewness is the third central moment of a distribution. This describes how the sample differs in shape from a symmetrical distribution. In other words, it is a measure of asymmetry of a distribution. When the scores are distributed strictly as per the normal pattern, the distribution is symmetrical. When most of the scores of a distribution are towards the left of the mode of the distribution, that is a positively skewed distribution, and when most of the scores are accumulated towards the right side of the mode of the distribution, it is a negatively skewed distribution. And here in this picture provided, you can see different types of distributions: a symmetrical distribution, a positively skewed distribution, and a negatively skewed distribution. And in a symmetrical distribution, mean, median and mode will be equal. In a positively skewed distribution, mean is higher than mode, and in a negatively skewed distribution, mean is lower than mode. Now you can see measures of skewness. Skewness can be measured in absolute terms as the difference between mean, median and mode. And for empirical purposes, the formula is skewness is equal to mean minus mode, or skewness is equal to 3 into mean minus median. The most widely used relative measure of skewness is called Pearson's coefficient of skewness. And Pearson's coefficient of skewness is a measure of skewness based on the difference between mean and mode, and it is denoted by SKP, and SKP is equal to mean minus mode divided by standard deviation. In practice, the value lies between -1 and +1. When SKP is equal to 0, the distribution is symmetrical. When SKP is positive, the distribution is positively skewed, and when escape is negative, the distribution is negatively skewed. The above formula cannot be used when mode is ill-defined. Then escape is calculated using the formula escape is equal to 3 into mean minus median divided by standard deviation. Coefficient of skewness can also be calculated using a formula escape is equal to sigma x minus x bar the whole cubed divided by n into s cubed, or it is equal to sigma d cubed divided by n into s cubed. And here x is the value of the variable, x bar is the mean, n is the number of times of occurrence of x, and s is the standard deviation. Then comes kurtosis. Kurtosis is known as the fourth central moment of a distribution. Kurtosis is the picketness of the frequency curve. It is the property of a distribution which expresses its relative picketness. It tells about the extent to which the distribution is heavier or light-tailed when compared to the normal distribution. And you can see that when you consider kurtosis, there are different types of distributions. You can say that there are mesokurtic, leptokurtic and platykurtic distributions. Kurtosis is a measure to indicate whether a distribution is normal, peaked or flat with respect to the probability distribution. It is said to be mesokurtic if the variable is distributed as per the expectation of a normal frequency distribution. If the curve shows peakedness higher than the normal curve, it is said to be leptokurtic, and if the curve shows a flat peak when compared to the normal curve, it is said to be platykurtic. And here you can see three pictures. The first one showing a mesokurtic distribution, a frequency curve of a mesokurtic distribution. The second one, the frequency curve of a leptokurtic distribution. And the third one, the frequency curve of a platykurtic distribution. And to measure skewness, there are certain measures developed, and usually two measures are used, and these measures were proposed by Karl Pearson, and they are known as Karl Pearson's measures of kurtosis. The measures are beta 2 and gamma 2. And the relationship between beta 2 and gamma 2 is gamma 2 is equal to beta 2 minus 3. Gamma 2 is 0 in the case of a mesokurtic distribution, lesser than 0 in the case of a platykurtic distribution, and higher than 0 in the case of a leptokurtic distribution. And by formula, beta 2 is equal to
sigma d raised 4
divided by n into s raised 4, or
sigma f d raised 4
divided by n into s raised 4. And gamma 2 is equal to beta 2 minus 3. And in the formula, of course, n stands for the number of times of occurrence of the variable x, and s stands for the standard deviation. D is x minus x bar. Now we can work out a problem on skewness and kurtosis. Data on yield of fruits from an orange farm in a year are given below. Find out the coefficient of skewness and measures of kurtosis of the distribution. The values of x are given. It is a continuous frequency distribution. It starts from 20 and ends at 160, means the production of oranges by different trees vary from 20 to 160, and there are several frequency classes. Each class has a particular frequency, and of course you are asked to calculate the measures of skewness and kurtosis, coefficient of skewness and beta 2 and gamma 2. So the first step, as you know, since it is a continuous frequency distribution, the first step is to find out the mid values of the classes, and we have calculated the mid values. And the mean of the distribution has been found out using the formula mean is equal to sigma fm divided by n, and if you calculate it, it is equal to 97, and n means it is sigma f, and if you are adding up all the frequencies, all the number of plants, you can see that there are 200 plants in the population. So n is equal to 200, and the middle values already we have calculated in the case of each class, and the mean, since the mean is also known, the first step is to calculate d. d is x minus x bar. In all the cases we have calculated it, minus 6, 7, minus 4, 7, minus 2, 7, 7, minus 7, 13, 33 and 53. And the next step is to find out the squares, d square. So you have calculated d square, and you have, of course, you have to multiply d square with f, since there are a number of plants in each class, and fd square is calculated here, and you have to calculate sigma fd square also. Sigma fd square has also been calculated. Then the next step is to calculate d cubed. D cubed is of course d squared into d, and in the case of d cubed it may be a positive value or a negative value depending upon the fact whether d is positive or negative. So you get different d cubed values, and the next step is you have to find out fd cubed and sigma fd cubed also you have to calculate. Then the next step is to find out d raised to 4. d raised to 4 is also to be calculated, and all the values of d raised to 4 will be positive, and fd raised to 4 also is also to be calculated, and sigma fd raised to 4. So now you have calculated the mean, the value of n, sigma fd squared, sigma fd cubed, and sigma fd raised to 4. And from sigma fd square you can calculate the second moment, means the variance, the second central moment. Sigma fd squared by n is the formula. And from fd cubed, from sigma fd cubed you can calculate coefficient of skewness, and the formula is sigma fd cubed divided by n into s cubed. S is the standard deviation. And from fd raised to 4 and sigma fd raised to 4 you can calculate beta 2. Beta 2 is equal to sigma fd raised to 4 divided by n into s raised to 4. S is the standard deviation. So now you can calculate each and every value. Variance can be calculated using the formula sigma fd squared by n, and sigma fd squared, since you have already calculated, it is divided by n, n is equal to 200, and you get variance as 1051, and you can calculate standard deviation. Standard deviation is the square root of variance, and it is equal to 32.4. And from sigma FD cubed, you can calculate coefficient of skewness. Coefficient of skewness is equal to sigma FD cubed divided by n into s cubed, and when you calculate it, it is equal to minus 0.22. And from sigma FD raised to 4 and from sigma FD, from sigma FD raised to 4, you can calculate beta 2, and the formula for beta 2 is sigma FD raised to 4 divided by n into s raised to 4, and s is the standard deviation, and if you calculate it, you are getting it as 2.31. And gamma 2 you can find out by minusing 3 from beta 2. So 2.31 minus 3 is equal to minus 0.69. So the coefficient of skewness is minus 0.22, and beta 2 is 2.31, and gamma 2 is minus 0.69, and the results show that coefficient of skewness of the distribution, since it is minus 0.22, the distribution is showing negative skewness, and since beta 2 is lesser than 3 and gamma 2 is negative, the distribution is Platy-Kurti. So you have now found out the second moment, third moment and fourth moment of a distribution, and that was about the central moments, the second moment, third moment and the fourth moment, which can be otherwise called variance, coefficient of skewness, and measures of kurtosis. Thank you very much.